So let's try a concrete example of this. And we'll do this top to bottom. And if you have any questions, please post them to the discussion board. This is a big deal. We'll use these ideas the rest of the semester to understand modern crypto routines. So here's the example. Alice and Bob are going to do a Diffie-Hellman key exchange, and so they need to agree on their parameters. So their public parameters, let's say their prime is going to be 167, and their special number mod p will be 41, okay? And just trust me, these fit the protocol. That really is a prime number, and this really is special. Whatever special means, don't worry about it, okay? So, of course, you would never use 167 in real life because it's only 3 digits long. That's too small. You would typically use a prime that has a couple of hundred digits, not just 3 digits, okay? But for the sake of this discussion, let's just use the prime 167, okay? So what does Alice do? Well, her job is to choose a secret exponent between 1 and 166, okay? So Alice chooses secret x equals 101. So that's her secret. X is going to be, for her, 101. And of course, nobody knows that. Not Bob, not Eve, not anybody, okay? So then she computes A, which is g to the x, all right? And so for us, that is going to be 41. That's g to the x, which is 101. And she works mod 167. You can check on your own modular calculator that 41 to the 101 is 125 when you work mod 167, okay? So Alice's A is 125. So she simply emails Bob, hey Bob, A is 125. And of course, the assumption is that Eve knows that too. She sees that email, okay? She sees that email. Next, Bob does the same thing. He selects his own secret. He chooses 32, okay? Then he computes his big B, which is g to the y, which is 41. That's everybody's g, to his own secret 32. And you can check that 41 to the 32 is 27 when you work mod 167. So he doesn't tell anybody in the world that 32 is his secret, but he does tell Alice that, hey Alice, B is equal to 27. So now Alice knows that, but of course so does Eve. So here's what Alice does to compute her secret. Remember, she computes b to the x. Alice computes b to the x. So b she knows because Bob just told her is 27, and she knows her own secret, which is 101, and you can punch this into your modular calculator and see that 27 to the 101 is 75. So Alice thinks the key is 75, all right? That's what she thinks the key is. What does Bob get, right? Well, Bob computes the key as a to the y. Well, Alice told him a already, it's 125. She also knows her own, he knows his own secret y, right? So he already knows a. He knows his own secret y is 32. No one else knows that. And so Bob computes 125 to the 32nd power, and he gets 75. So look what happens. They get the same answer. They both get 75. So now Alice and Bob know that their common key for this encryption scheme would be 75. Whatever scheme they're using, they have now established a key for it at 75. So they have both generated the same secret key, and they've done it right in front of Eve's own eyes. Okay, so this is kind of amazing, right? Let's talk about a few things going on with Diffie-Hellman key exchange here. Okay, so again, to summarize, Alice computes her key by using 2 ingredients: the B that Bob told her and her own X. Everybody in the world knows B, but only Alice knows X. Same thing for Bob. He computes the key using only 2 ingredients: the A that Alice told him and his own secret Y. Okay, everybody knows A, even Eve, but only Bob knows Y. All right? So even though Alice doesn't know Bob's Y, and Bob doesn't know Alice's X, they can still generate the same key. That's, to me, the amazing part. They don't know each other's secret, but they can still generate the same key. Right? Here's the important thing. The secrets they use, Alice used a secret X, Bob used a secret Y. Those secrets, notice, those secrets never went over the open line. Those secrets never left their desks. Right? That's the power of Diffie-Hellman key exchange. The secret information that they use in the recipe for this key never leaves their desk. It never has to go out in public. That's huge. Since they don't know each other's secret, this is even safe from each other. Okay? Neither one of them knows how they generated the same key. Alice does not know Bob's secret, and Bob does not know Alice's secret. What does Eve know in all this? Eve knows the public prime P, the public special element G, and she knows A and B that were passed over the line by Alice and Bob respectively, right? But she doesn't know X or Y. And the big question is, without that knowledge of X or Y, can Eve get the key? You hope not, right? And the answer is no, she can't, not really. And we'll have to look at this in a future lecture. It's not obvious. You're not supposed to understand this yet. It is not obvious why Eve cannot do some other fancy math and get the key. That's not clear, okay? So you're going to have to read this a few times to really get it. It's hard to think about, but it's worthwhile. So the last thing I want you to do is participate in a Diffie-Hellman key exchange with me in a Canvas quiz. So what I've given you here is a recipe for you and I to do a Diffie-Hellman key exchange. You'll be Alice and I'll be Bob. Okay, I've already conveyed to you my public element B is 76020, and here's our prime, it's a 6-digit prime, and here's our special G. I would like you to pick your own secret X because you're Alice, compute your A value, and post your value of A to make it public. The whole point is that A can be public, so post it out loud to the Canvas discussion board for this handout. All right, don't post anything else. Don't post your X. Don't post our key, but post your value of A. Then I want you to walk away and compute what you think our key is and put it in the Canvas quiz, and I'll grade it as soon as I can. Okay? So try it out, see how it goes. If you have any questions, post them.